Besides knowing where the center of a set of data is, another important piece is looking at how much variation, or on the other side, how consistent the data is. This is because if there's a lot of variation in the data, and we're trying to use this to make decisions based on a sample, if there's a lot of variation, we're less certain about what's going on with our sample, because maybe we just got something pretty lopsided due to the amount of variation. Another thing that we want to be considering when we're looking at variation is manufacturing. If I am building something with something like these bolts, nuts, and washers that we have here, we want to make sure these things fit together. So it's not enough that this bolt has an average diameter that fits into this washer. It needs to be consistent, right? This bolt needs to fit into the washers almost every single time, right? If we're having things that don't fit, that's a big problem in the manufacturing process. And I said washer, but that's a nut. So the bolt needs to fit into the nut, and the washer needs to fit as well. Not as precisely as the nut. So if we're looking at ways of measuring variation, there's several ways we can do that, and as with the mean, median, and mode for measuring our central value, some of these are better in certain circumstances than others. So the range, like the mid-range, is useful as a quick calculation, something that we look at just to see what's going on in seconds. It's not likely going to be our final answer, though, when we're trying to figure something out, because if we have a single outlier, this is greatly going to affect our range. So if you look at these two sets of data, right, this one is almost consistent, except it's got this one outlier. So 9 of the 10 values are really close together. That 10th value is completely out to lunch. So it makes it the range really, really high. But in the second set of data, we have things that are a little more all over the place, but a smaller range because we don't have any that's a big outlier. So the consistency being measured by range, not a very good calculation. And just in case you needed a quick where did that number come from, right? Highest minus the lowest for the range, top and bottom values. So 20 is our highest of all these values, minus 1 gives me 19. 20 is also the largest of this data set, minus 14 gives me a range of 6. So a better measure of consistency is looking at standard deviation and variance. And these two are very linked because variance is just the square of standard deviation, or if you want to say it the other way around, standard deviation is just the square root of variance. So these get used in statistics as a measure of how far away the average data point is. Right? If you look, in our calculation, we have x minus x bar, so that's our data point minus the mean. And then we square it and square root it. And you might think, well, why do you bother doing that? Squaring and square rooting just cancel each other out. The reason is it makes it looking at the absolute value. We also aren't strictly taking an average because we're dividing by n minus 1, and that is also under the square root. So it's kind of based on the average distance that a value is from the mean, right? X minus x bar is how far it is from the mean, but it's not quite an average. So standard deviation and variance get used a lot in statistics, and really they're used as a relative value. So is this set of data more consistent, in which case it'll have a smaller standard deviation, or is it less consistent, in which case it'll have a larger standard deviation? The second formula here, you might think that's a completely different formula, and it certainly looks completely different, but it actually gives you the exact same answer. So we will do an example both ways so you can see you do get the same answer. Some people prefer one over the other. We'll also mention the fact that you can calculate these things using Excel. So those are pretty we'll look at the examples. They're pretty complex calculations, but if we set them up in tables, it actually is not too bad at all. So one of these things you got to do step by step and work your way through it. We will also look at the formulas for frequency tables, which again look rather different, but can be calculated using tables. The population standard deviation I will mention, because if we are calculating for a population, we need to make sure we are dividing by n, not n minus 1. Also, as with our mean, we have two different symbols. So the sample, our symbol is again the Roman letters, a little s, and the population symbol is the Greek letter sigma. And some of you might be thinking, hey, I thought that summation sign was a sigma. What do you mean this thing's a sigma? Remember that alphabets can have uppercase and lowercase, so just like we can have an A that looks like this, or we can have an A that looks like this, they're both A's. They look kind of different, but they're both A's. So likewise, we have sigma, that means the sum, and we have sigma, that means the standard deviation. As I mentioned, variance is just standard deviation squared, whether we're talking about the sample variance or the population variance. Always when you're comparing these two, our sample standard deviation does give a higher value because we're dividing by n minus 1. And the reason for that is we always have a level of uncertainty when we have a sample. So we divide by n minus 1 to account for that uncertainty. And we refer to it as the unbiased estimator. So let's take a look at an example. And as I mentioned, we're going to do it using each formula. So the first formula is that one with the x minus x bar squared divided by n minus 1. So if we have our set of data, the first thing we need to do is take this data set and calculate the mean. So remember, we go x minus, sorry, not x minus, sum of our x is divided by the number. So we add these up and divide by 6. I'm going to assume that you can do that and just jump to the answer. Again, double check by doing the calculation to make sure you get where that comes from. Now this is one, because we end up dividing by 6, we get a repeating decimal. Good idea to learn how to use the memory button in your calculator, because if you look at our formula, we need to go x minus the mean for each one of these 6 data points. So we're going to have to subtract this value for each one. And since this isn't our final answer, we don't want to round it, right? Because it's not our final answer. We round at the very end. So keeping that number in your calculator, in the memory button, we can go x minus the mean for each value. So if we take the first one, that becomes 259 minus 246.33 repeating, and then we have to square that. So we get 160.444. Again, I'm not showing all the digits, it's repeating. We do the same thing with the other 5 data points, right? So we subtract 262 minus that mean value, 246 point, and again, it's better to have that in your memory button rather than retyping it in to your calculator. And then don't forget to square the result to get your final answer, which in this case is going to be 245.4 repeating. And that should have been a decimal. My typing skills. So take a moment, pause the video, make sure you can get that calculation, try the next 4. And once you've tried the next 4, hopefully you've done that, we can restart and calculate those values. Put in those values, I should say. So if we look at our formula, we need the sum of all those values we just calculated divided by n minus 1. So the sum of all those values, 1183.3 repeating. So we plug that into here, we do the calculation, and I'm actually going to show an extra step I wouldn't necessarily expect you to show. And that's the value we get before we take the square root. A pretty common mistake is to forget to take the square root, so that's why I'm showing that value. And then when we do take the square root, we're going to get some value that has a lot of decimals to it. Like with the mean, we round our standard deviation to one more than our raw data. So here our raw data was all to the nearest Newton, so we're going to go to the nearest tenth of a Newton for the mean. So there's our calculation for the first one. If we look at the second formula, I mentioned that although the formulas look very different, they give us the same answer. Now there's a couple of things in this formula that sometimes give people problems. One is that we have sum of the x squared. When I read it out loud, they both look like sum of the x squared. But whether I have the brackets or not makes a big difference. So this is sum of the x's in brackets. That tells us we have to add up the x's first and then square a result. This one is sum of the x's squared, no brackets, order of operation tells us square first, add second. So the table part of this is a little more straightforward. The formula, you do have to pause and think about which one goes where. So our x value squared, right, we just go to 59 and take that and square it, and we get a value. Again, I would suggest you pause the video, calculate all these 6 values. Once you have the 6 values, we also need the sums. So we're going to put totals, like we put one total here, we're going to put both totals in this one. So pause the video, do the calculations, come back. So there should be our squares. If we look at our totals, whoops, that did not do what I wanted it to. Let me try again. There we go, that's better. All right, we add them up, we get that. So we want to put those two totals into our formula. So our n is still 6, right? We still have those 6 data points. Sum of the x squareds is going to be this large total that we've got. Sum of the x's is this total that we've got here, but then we're going to square it. If you mix those two up, you will know very quickly, because underneath our square root, you will end up with a negative sign. And we know that when there's a negative under a square root, something's gone wrong. So in this particular case, or at least in this application, something's gone wrong. So you should end up with a negative under square root. We don't need any imaginary numbers here. So we plug those values in, do the calculation. Again, I suggest you pause and make sure that you can actually get this value. We get that same value underneath the square root that we got before. And so when we take the square root, it makes sense we're going to get the same value of 15.4 when we round it, newtons. So it doesn't matter which formula we use, both work. You can also use the statistical functions on your calculator or the statistical functions within the Excel. So when you're looking at those, one thing to be careful about is we have 2 standard deviations, right? We have the population standard deviation and we have the sample standard deviation. Excel and your calculator as well have 2 different standard deviations. So make sure you know which one's which. The sample one's always going to be larger than the population one. And the vast majority of the time we are working with samples. So we're going to want the sample standard deviation more often than we want the population one. So I already mentioned round one more decimal place in your original data. I didn't mention this. The units for standard deviation are the same as the units for your original data. If you look at what we do, that makes sense because we square this difference, which is going to have the same units, but then square root it. So square and square root are going to be back to our same units that we started with. Now, there's a rule of thumb that is just a quick way of checking that your answer's in the right ballpark, which is that the range is approximately 4 times the standard deviation, or the way we're more often using it, the standard deviation is approximately 1/4 of the range. And that's not going to get you the exact value, just like when you take a mid-range to see if your average is correct, right? You might have a value of 69.4 and your actual average is 71. When you do that sort of thing, whether we're talking about this range rule of thumb for the range or looking at the mid-range to estimate a mean, it's just telling you, am I in the right ballpark? What it will catch is things like, I forgot to take the square root, right? Because if you're thinking that this average should be somewhere around, say, 12, and you're getting an answer of 237, you should say, wait a second, I've done something wrong. On the other hand, if your range rule of thumb gets you a value of 12 and your actual value is somewhere like 15, you can say, okay, that seems reasonable. They're somewhat close to each other. They're in the same ballpark. Also, another thing to mention is that typical or usual or normal, lots of ways of saying this, values fall within 2 standard deviations of the mean. So if we take our mean and we add 2 standard deviations or subtract 2 standard deviations, we get most of the population. Things that fall outside of that are considered unusual. So for instance, if we were taking height data and we had someone whose height was really tall, we might find that they're more than 2 standard deviations away from the mean. So that's going to be those really tall people that have to, say, duck through the doorway when they get onto the C train. Likewise, the really short people and adults who have to jump to sit on a regular chair because they're not set up for the unusual, they're set up for the typical. So to say that someone falls outside of those 2 standard deviations doesn't make it an impossible value, it just makes it an unusual value. There's 2 other rules of thumb that we can look at with that. One is Chebyshev's theorem that says the proportion of values that falls within a certain number of standard deviations is at least, and keep in mind it's not equal, it's at least 1 minus 1 divided by k squared. So if we're doing that with 2 standard deviations, we would say 1 minus 1 divided by 2 squared. And so that would be 1 over 1/4, 1 minus 1/4, which is 75%. If we did it with 3 standard deviations, we'd put 3 in for k, which gives us 1 minus 1/9, or approximately 89% fall within 3 standard deviations. So you can see, right, very few fall outside that, and that's at least. It might be that all of the data fall within there. We also have what's called the empirical rule, but be careful, the empirical rule only applies to a Bell distribution. So the empirical rule, right, if we have a skewed data set or some other distribution, is not necessarily going to apply. So if something is approximately normal or a Bell distribution, we can say about 68% of the scores fall within 1 standard deviation, about 95% fall within 2, and 99.7% fall within 3. So Chebyshev's theorem works no matter what distribution we have. The empirical rule only applies to a Bell distribution. Like with the mean, we do have a variation on the standard deviation formula, and that's when we're looking at a frequency table. So when we have a frequency table like this, we can put it into, again, there's 2 variations of the formula. I'm going with that second variation. I didn't mention back up here, but I will mention it now. Of these two variations, the second formula is sometimes referred to as the shortcut formula because most people find that second formula is quicker. As I mentioned though, it doesn't matter which formula you use, they both get you to the right answer. So the frequency table formula that I used is that shortcut formula. Again, there is a frequency table that's the longer version of the formula, and you can use that and it will get you the right answer, but I prefer to use the shortcut formula, so I'm going to do the example with that. So for each value, we need to calculate f times x, or the frequency times our score, and f times x squared. Now be careful, there is no brackets here, so only the x's squared. So I would point out this is f times x squared, not f times x squared. So be careful, because that's a common mistake again. So just like with our other frequency table, we have a range here. So if we want to know our value for x, we have to find our class marks. So we would go 3.5 plus 7.4 divide by 2 to get our first class mark. And likewise for each of the rest. So we get these class marks. Again, if you need to pause, calculate those to make sure you get where they come from, do that. So for each one of these calculations, each one of these rows, I should say, we're going to need to do two calculations, frequency times x and frequency times x squared. So for this first row, that becomes 6 times 5.45 and 6 times 5.45 squared. Again, pause, do the calculations for the next few, see that you can get the correct numbers. Assuming you've paused, here we go with the answers. And we do need totals for each of these. So we need the total f times x for this part of our formula, right? It's the sum of f times x. And we need the total for f times x squared, right, for this part of our formula. We also need the total frequencies. Remember, our n is not going to be 1, 2, 3, 4, 5, 6. It's going to be 6 plus 17 plus 9 plus 2 plus 1. So we need all those totals. So again, you may want to pause while you calculate them. And so we get these values. And I do have a note here, as I mentioned, sum of our frequencies is the same as saying n. So we plug that into our formula. And I need to scroll up so you can see what I'm doing. So our sum of fx squared is going to be our 4,892, etc. Our sum of f times x is going to be our 382.75, and then we'll square it. Our n is 35, and our n minus 1 is 34. And I see I need to make a quick change because I've used a slightly different variation of the formula. So let me do that here. Sorry for the delay, but hopefully you're calculating it. And So we get an average of 4.65. Our units here are a little unusual. Liters per 100 kilometer. That's typically how gas mileage is reported. In Canada, anyways. In the United States, it might be miles per gallon. Again, we need to check, does this seem reasonable? So we can look at that range rule of thumb, which says if we take our range and divide by 4, we should get approximately the standard deviation. So our range here, our highest value 27.4, our lowest value 3.5. So we subtract that and divide by 4. We get 5.975. Obviously way too many digits for a quick estimate, so about 6. And our actual answer was closer to 5, but it wasn't, for instance, 20. So if we had forgot to take our square root, we would see that, oh, those aren't close. So these are close enough that, yes, we can check that it's in the right ballpark. It's not right on, but it's in the right ballpark. Okay, so there is our measures of variation.